Okay, so let's unpack this. I want you to picture something with me for a second. Imagine you're looking at a map of a vast archipelago. You've got these separate, distinct islands scattered all across the ocean.
Okay.
One island is populated entirely by the engineering department. Another one, maybe a bit louder and sunnier, that's purely the sales team. And way off in the distance, on a foggy rock, you've got HR.
I think HR would probably resent the foggy rock description, but for the sake of the analogy, let's go with it.
Yeah, let's go with it. In the networking world, these islands,
Yeah.
we call them VLANs, right? Virtual Local Area Network.
Exactly.
And the whole logic behind building these islands, these VLANs, is isolation. Correct.
That's the main goal.
You want them secure. You want them, quiet. You don't want the sales team's constant chatter and broadcast traffic spilling over and interrupting the engineers who are trying to do deep work.
Exactly. It creates a boundary. It keeps the noise down and the security up. It's just a clean, organized way to segment a network.
But here's the flaw in this perfect map. The islands have no boats.
None. They are completely, totally cut off.
So if a computer in engineering on Island A wants to send a crucial file to a computer in sales on Island B,
They can't.
they can't.
Right.
They can shout from the beach all they want, but the data is not going anywhere.
Because layer 2 switches, the devices creating these islands, they're really strict. They respect those boundaries. By default, they will not let traffic cross from VLAN 10 to VLAN 20.
So we have a massive dilemma. I mean, it's a huge dilemma. We need the security and organization of the islands, but we still need to build bridges between them so business can actually happen.
Right.
And that brings us to the topic of today's deep dive. We are looking at inter-VLAN routing.
The evolution of connectivity, it really is a story of how we went from these clunky physical solutions to high-speed virtual ones.
We have a stack of technical modules here covering everything from what they call the dark ages of legacy routing all the way to the modern Ferrari of layer 3 switching. We're going to trace how network engineers solve this island problem, look at the specific commands to make it happen, and here's where it gets really interesting. We're going to look at why it breaks.
Because in networking, if it can break, it absolutely will break.
It effectively always does. So what's our mission today?
Our mission is to understand the 3 distinct architectures for bridging these gaps. We need to move from the physical constraints of the past through the virtualization era, and then finally to hardware acceleration. And critically, we need to understand the troubleshooting philosophy so you don't crash the network when you try to configure it.
All right, let's jump into the time machine. We're going back to phase 1. The source material calls this legacy inter-VLAN routing. But honestly, reading through these notes, it feels a bit like the Stone Age.
It definitely feels that way now, but you have to remember, at the time, it was the only logical way to solve the problem.
So paint the picture for us. We got our switch with our separate VLANs engineering and sales. How did we get them to talk before we had all this fancy virtualization?
Well, we used a router. That's that layer 3 intervention we mentioned. Routers are designed to forward traffic between different networks.
Okay.
So in the legacy model, we relied on a very, very strict physical rule. 1 VLAN equals 1 physical port.
1 VLAN, 1 physical port. That sounds incredibly literal. So if I have a blue cable for engineering, which is VLAN 10, and an orange cable for sales, VLAN 20.
Then you need 2 physical interfaces on your router.
Wow.
You plug the blue cable into interface G000 and the orange cable into G001. The router just treats them as completely separate physical worlds. Traffic goes out of the switch, up the blue cable, gets routed, and comes back down the orange cable.
Okay, that sounds functional. I mean, it makes sense visually.
Yeah.
But why is this considered obsolete in big, bold letters in our notes?
Think about scale. Just think about scale.
Yeah.
Imagine you are a large university or a corporate campus. How many VLANs might you have?
Oh, I don't know, 50, 100.
Easily. Now imagine trying to buy a router with 100 physical Ethernet ports.
Does a thing like that even exist?
Not really, and if it did, it would be the size of a refrigerator and cost more than the building itself. This is what we call the physical wall.
Wow.
It creates a scaling nightmare. You just immediately exhaust your hardware capacity.
So functionally sound, but
Physically impossible to scale.
it's like trying to charge 100 phones, but you only have 2 outlets in your house.
That's a perfect analogy. So the industry realized we needed a way to kind of cheat the physics. We needed to stop relying on physical cables for every single network.
And that brings us to phase 2. This is what the notes call the smart economy solution. It has one of my favorite names in all of tech, router on a stick.
We call it ROAS for short.
Router on a stick. It sounds like a deep-fried fairground snack.
Mm.
I'll take a corn dog and a router on a stick, please.
Yeah, it does.
But jokes aside, this really changed the game for, like, small and medium businesses, right?
It really did, because it solved that port exhaustion problem. Instead of 100 cables for 100 VLANs, we use one single physical wire, the stick, to connect the router and the switch.
Okay, hold on. This is where I get a little skeptical. If I have confidential engineering traffic and loud sales traffic all pouring into the same wire, aren't they going to mix? How does the router know which packet belongs to which department? It sounds like a collision waiting to happen.
That is the million-dollar question, and the answer is the 802.1q standard. We call it trunking.
Or tagging.
Right, tagging. To understand this, just imagine you're at a busy airport checking bags. You have a black suitcase, and I have a black suitcase. To the naked eye, they look identical.
Okay.
But the agent slaps a tag on yours that says SFO for San Francisco, and a tag on mine that says JFK for New York.
Right.
The conveyor belt behind the desk, that's our stick. It carries everyone's bags all mixed together. It doesn't care whose bag is whose. But when they get to the sorting facility, that's the router, the machine reads the tag.
Oh, I see.
Oh, this one is tag 10. It goes to engineering. This one is tag 20. It goes to sales.
So the wire is shared, but the identity of the data is preserved by that little digital tag?
Precisely. The router sorts the traffic based on the tag, routes it, re-tags it for the destination, and sends it right back down the stick.
That makes a lot of sense. But, and here's the catch, you have to tell the router how to read those tags. It doesn't just know automatically.
No, it doesn't. And this is where the configuration gets clever. We take that one physical port, say Gigabit Ethernet 001, and we logically slice it into pieces. We call them subinterfaces.
Subinterfaces. So G001 becomes what, like?
It becomes G001.10 for VLAN 10 and G001.20 for VLAN 20.
Ah, I see. So we are creating virtual interfaces for our virtual LANs.
Exactly.
Now, looking at the configuration notes here, there's some serious gotchas with router on a stick. It seems like the order you do things in matters a lot.
It matters immensely. A really common mistake is trying to put the IP address on the subinterface right away. You type interface G001.0 and then you immediately try to add the IP, but the router will reject it because you haven't told the router which tag to look for yet. It's like trying to file a document before you've even labeled the folder. You have to define the encapsulation first.
So the command is encapsulation.1q10.
Yes. That command tells the router, hey, this virtual slice is specifically for traffic tagged with ID 10. Then and only then can you add the IP address.
Okay, that's a good tip. And there's another trap on the router side, specifically with the main physical interface.
Oh, yes, the shutdown state. This drives people absolutely crazy. You can configure your subinterfaces perfectly, tags, IPs, everything. But if the physical parent interface, the actual plug, is shut down, none of the subinterfaces will work.
It's like wiring a house perfectly, but you forgot to flip the master breaker.
Exactly that. You have to issue the no shutdown command on the physical interface to power up the whole stick.
Now, quickly, on the switch side.
Yeah.
You said this stick carries multiple VLANs. Does the switch need to know that?
Absolutely. The port on the switch that connects to the router must be configured as to trunk. If you leave it as an access port, which is the default, it won't send the tags.
And if the tags are missing?
The router rejects the traffic, is expecting those airport luggage tags we were talking about. If a bag comes through with no tag, the router just says, I don't know what this is, and drops it.
So reader on a stick seems great. It saves ports, it's cheaper. But our notes say it has a limit. They say it's generally unsuitable for networks with more than 50 VLANs. Why is that?
Bandwidth contention. You might have saved ports, but you're still funneling all of that traffic engineering, sales, HR, everyone through one single physical cable.
The stick becomes a bottleneck.
A huge bottleneck. If engineering decides to download a terabyte of data, the sales team is going to feel it. Plus, the routing is all happening in software on the router's CPU. It's smart, but it's relatively slow compared to what came next.
Which leads us perfectly to phase 3. The notes call this the Ferrari of inter-VLAN routing, the enterprise standard, layer 3 switching.
Now we're talking speed.
So physically, how is this different? We've got no stick, no external router.
Right. The biggest difference is that we remove the external router entirely. The routing engine is pulled inside the switch itself, but it's not just about location. It's about the brain that's doing the work.
I see the acronym ASICs highlighted here very heavily.
Yes, application-specific integrated circuits. This is the secret sauce. In the router on a stick method, a general-purpose CPU has to think about every single packet. It's software-based, Open packet, look at IP, look at table, rewrite header. It takes time.
Like me doing long division with a pencil and paper.
Exactly. But ASICs are hardware chips where the logic is literally burned into the silicon. They don't have to think in the traditional sense. They handle the switching and routing logic electrically at wire speed.
So it's the difference between me using a pencil
And using a calculator where the answer appears the instant you press the button.
that explains why the throughput is so much higher. We aren't just moving the router, we're changing the actual physics of the processing.
And the latency drops to almost nothing because the data doesn't have to leave the switch, go up a cable to a router, and come all the way back. It's all internal.
Let's talk about how we configure this beast. In ROAS, we had subinterfaces. What do we have inside a layer 3 switch?
We use SVI switched virtual interfaces.
These are the interface VLAN 10 commands we see.
Correct.
Yeah.
You aren't slicing up a physical port anymore. You're creating a virtual gateway interface that kind of floats inside the switch's logic. You type interface VLAN 10, give it an IP address, and boom, that's the default gateway for everyone in VLAN 10.
Okay, but here is where it gets really interesting. There is a warning box in our source material that is practically screaming in red text.
I know exactly which one you're looking at.
You spend thousands of dollars on this high-end layer 3 switch. You configure all your SVIs, you set your IPs, you plug everything in, and nothing works. The islands are still isolated. It's dead on arrival.
It's the classic panic moment for a network admin.
Why? Is the hardware just broken?
No, the hardware is having an identity crisis. See, by default, a switch thinks it is a switch. It wants to move frames at layer 2. It doesn't want to route packets.
So you have to force it.
You have to flip the switch in its brain. You have to enable the global routing capability.
A magic switch.
The command IP routing, just 2 words. If you don't type IP routing in global configuration mode, that expensive layer 3 switch is just a fancy, very expensive layer 2 switch.
I can just imagine the frustration. I bought the best gear. Why isn't it working? Did you type IP routing? Ooh.
It happens more often than you would think. It's the first thing I check when someone calls me about a layer 3 switch issue.
Now, there's one more piece to the layer 3 switch puzzle. Eventually, this traffic needs to leave the building, right? It needs to get to the internet or a core router. But we just said layer 3 switches use virtual interfaces. So how do we connect to an ISP router?
We use something called a routed port.
How is that different from a normal switch port?
A normal switch port operates at layer 2. It expects MSE addresses and switching logic. But on a layer 3 switch, we can take a physical port, say G001, and tell it, stop being a switch port.
Literally. The command is no switch port.
Exactly. No switch port. That one command just strips away all the layer 2 functionality. Now, you can assign an IP address directly to that physical interface, just like you would on a router. It becomes a point-to-point layer 3 link.
And that is incredibly versatile. So if we step back and look at the showdown, we've got router on a stick versus layer 3 switching.
Right.
RAS is low cost, uses your existing gear, but it has that bandwidth bottleneck. Layer 3 switching is higher cost, specialized hardware, but you get that high throughput.
So the rule of thumb is pretty simple. If you are a small shop, maybe fewer than 50 VLANs, and you're on a budget, router on a stick is perfectly fine. It works.
Right.
But if you are a campus, an enterprise, or you have high performance needs where latency really matters, you need layer 3 switching.
Okay, we built the network, we've chosen our architecture. Now, inevitably, something stops working. Let's move into the troubleshooting philosophy.
This is my favorite part, the methodology.
The source material presents a troubleshooting triangle. It implies a direction.
Bottom up. Always bottom up. You start at layer 1.
The physical layer.
Is the cable even connected? Are the link lights blinking? It sounds so silly, but you'd be amazed how many people spend hours debugging routing tables when the cable is simply unplugged or plugged into the wrong port.
Or the dog ate the fiber optic cable.
Exactly. Or someone rolled their chair over it. Once you verify layer 1, then you move to layer 2, VLANs and trunks.
And this leads us to scenario 1 in our notes. The ghost VLAN. It sounds a little spooky.
It's a very stealthy error. Imagine you've configured your ports. You put ports 1 through 10 into VLAN 10, but when you plug a computer in, it gets no connection, no light, no traffic, nothing.
But I assigned the ports. I typed switch port access VLAN 10.
You assigned the ports to VLAN 10, but did you ever create VLAN 10?
Wait, I have to create it separately?
Yes. The switch maintains a database of all the allowed VLANs. If the switch doesn't have LAN 10 in its database, those ports you assigned are effectively in limbo. They are assigned to a ghost.
So how do I catch that?
The check is show LAN brief. If you don't see VLAN 10 listed in that database, it doesn't exist, and those ports are basically dead.
And there's a little quirk here about activating it too, right?
Yes. When you type VLAN 10 to create it, you enter a specific configuration mode. The VLAN doesn't actually become active until you type exit to leave that mode. You have to exit the mode for the creation to actually take effect in the database.
That is a very subtle catch. Okay, so layer 1 is good, layer 2 is good. Now we look at layer 3.
IP addresses, subnet masks, routing tables.
Let's look at scenario 2, the mismatch. This one seems specific to router on a stick.
This is a logical mismatch that drives admins crazy. Let's say you are setting up your subinterface for VLAN 10. You name it G001.10. You give it the IP address 192.168.1.1. Everything looks like it's for VLAN 10.
Right, I'm being organized.
But when you type that encapsulation command we talked about earlier, the one that sets the luggage tag, you made a typo. You typed encapsulation.1Q100.
Oh, so the name of the interface says 10, the IP says 10, but the actual tag...
The tag says 100. So traffic arrives from the switch tagged with 10. The router looks at it and says, well, I don't have a sub-interface for tag 10. I only have one for 100, and it just drops the packet.
And you're staring at the config, seeing interface 10 and IP 10, and thinking you're going crazy because everything looks right.
Exactly. You have to remember, the interface number, like the .10, is just a label. It's cosmetic. It doesn't dictate the tag. The encapsulation command is what dictates the tag. They have to match.
So how do we prove it's actually working? A functional network is a verified network.
Two main tools. First, the ping. Can you ping the gateway? Can you ping across the VLANs? If yes, you're usually good.
And if not?
Then you look at the brain. You run showbrute. You need to see if the router actually knows about the connected networks. If you see the codes C for connected for both your VLAN subnets, the router is ready to do its job.
If the route isn't there, the router can't route it. Simple as that.
Precisely. If the router doesn't know the destination exists, it just drops the packet.
So let's summarize this whole journey. We started with the physical walls of legacy routing. Too many cables, too few ports, huge costs.
Then we moved to the stick, virtualizing that connection with 802.1Q tags to save hardware. It was a huge leap forward, but it came at the cost of bandwidth contention.
And finally, we arrived at the layer 3 switch, using ASICs and internal SVIs to route at the speed of light, or at least the speed of wire.
And remember, whether it's a clunky old router or a shiny new switch, the logic is always the same. You separate the traffic for isolation and you route the traffic for connection.
That connects back to the bigger picture really nicely. The technology changes. We go from cables to chips, but the fundamental need for that controlled connection stays the same.
It does. It's always about balancing security with accessibility.
Before we wrap up, here is a thought to leave you with. We spent this whole time distinguishing between switching at layer 2 and routing at layer 3. But if modern layer 3 switches are handling routing internally, using hardware ASICs, and doing it just as fast as switching, at what point does that distinction just disappear?
That is the big question. In modern network design, especially with things like software-defined networking, that line is getting blurrier every single day. We might reach a point where switching and routing are just two words for the same basic action.
Something to mull over while you're checking your cable connections. That's it for this deep dive into inter-VLAN routing. Thanks for listening.
Happy rooting!